value. Now, all this is we're flipping it upside down, moving it over a little bit and up. Um, if you want to think of it that way. Hopefully, that didn't confuse you at all. But, just a second, I'm going to move this here. So we know that this is symmetrical. Now what we want to find is how does the distance change with the angle, assuming that we have some sort of arbitrary velocity. First, what we'd have to find is the relationship between the angle and the distance. Now, between the angle, velocity, and the distance, and then we can take out the velocity later and find the relationship strictly between the angle that we throw it at. So the distance and angle, we're going to go velocity and angle to distance, and then we're going to go angle to distance. And then from there, find at what point or at what angle is the best to throw it at. Now, first thing we need to do, like I said, is find the velocity, angle, and distance relationship, which is determined by this. So let's say we want to find this point. Where does this parabola intersect the x-axis? Well, it intersects at 2 points. And once again, if you've ever worked with parabolas, you'll know that if it intersects the x-axis at 2 points, which most of them do, it's eventually going to come down to a quadratic equation where you're then going to have to factor it out into you're going to have to factor it out into two different coefficients that are set to 0, and then you'll have two different values for x, and you'd have to pick one. But I find that way more complicated than simply doing this. I just proved to you over here. Hopefully I did it well enough, but that parabolas are symmetrical. So if we can find this very tippy top right here, and the x value of that very tippy top, all we have to do is multiply that by 2, and we get the x value for the and we get this x value right here. Now, if we notice, there are only one of these points and two of these points, so it would be much easier to simply find this one point and then extrapolate from there the endpoint here. Now, what we're going to do is say, well, how do we find this tippy top right here? There's, well, we can't do it strictly algebraically because I tried. Well, I did it, so I mean, I guess you can. But it's much easier with calculus, so I'm going to show you exactly how we do that. Now, what we're going to do is we're going to find the maximum of this curve, which is the highest point along this curve, which is almost completely dependent on y of t. So if you'll notice, the derivative of this function, or how quickly you're moving along y, is decreasing. Okay, it's getting flatter and flatter and flatter. Okay, so at first you're going up very, very fast, then as gravity pulls down on it, it starts to slow down, comes to a stop, and then falls down. So your slope is decreasing by the magnitude of the force vector g times t squared. And what I want to find is at what point does the velocity in the y direction equal 0? Because at 0, that's when you reach the very top of your arc, and then you come right back down. You know what I'm talking about. If you've ever thrown a ball up in the air, you notice that it kind of seems to slow down, stay there for just a little bit, and then fall down. So what we're going to do is we're going to find the derivative of this function, which I think we do. Wait a minute, do we need to find the derivative? Yeah, we do. Okay, sorry. So the derivative of wait, wait no, sorry. If yt equals vi sine fish times t minus gt squared, then the derivative of that, y prime of t, equals vi sine fish minus 2gt. That's a simple derivative. I mean, you've got some trigonometry in here, but other than that, that should be pretty easy for most of you in at least Calculus 1 to do. And all that's saying is finding the slope of the velocity vector in the y direction, or how fast, all this is how fast is the object moving in the y direction with respect to time. So at any point in time, if we give it a point in time, and the velocity and angle that we threw it at initially, we can find how fast it's moving in the y direction at that infinitely small point in time. Okay, I just drew a little dot to illustrate just how small it was. It's much smaller than the dot I drew. Um, so what we want to do is we want to find the point at which the velocity in the y direction equals 0. Because at that point you start to get a negative velocity in the y direction, which means that you're falling down. Um, so all we have to do is say 0 equals vi sine fish, or alpha, 2gt. Now, all we do is, we're just going to simplify this and say, add 2gt to both sides, 2gt equals vi sine alpha. So we've just changed the question from when does the velocity in the y direction equal 0 to when does vi sine alpha equal 2gt. Well, we can't find the x value right now, so we're going to find the time at which it reaches that point. And then from the time we're going to find the x value, which is going to be much easier. So all we're going to do is divide each side by 2g, which will give us t, or time of apex in this case. The time of the apex. You could just say t, but I mean, we're going to be more specific. Going to label that apex y point. So t of a, that's the t of a. So if t of a, or the time of the apex here, I'm going to draw a little box around it because that's really important, equals vi sine alpha 2g, and all we need to do to find, and like I said, this parabola is symmetrical, so if we can find the midpoint right here, then we can find that point by simply multiplying the midpoint by 2. So if the time of the apex equals vi sine fish over 2g, then all we have to do is multiply that by 2, which means that that 2 cancels out. And the time of the final point, and the time when you reach the x, the t of f, or t of final, the final t, equals vi sine alpha over g, which I think she actually showed in that video. So the time of the final, so the time when you finally hit the ground is equivalent to the velocity you threw it at times the sine of the angle you threw it at divided by g, which is a very nice equation. It's very satisfying. At least I like it that way. Now, if the time of your landing, I guess, is determined by that equation, all we have to do is factor that into the t function here of x of t. So if t of f equals that, then x of f equals simply vi sine alpha, or fish, I like fish better, g, times, no, I'm not even going to put the times there, times vi cosine alpha. Wait a second. Why is that there? Yeah, vi cosine alpha times t. Wait, no, not times t, because we're substituting t. Sorry, don't erase that. We're substituting t for this, so I mean it really should be on the other side, but let's keep on going. No, I'm gonna rewrite it. Okay. So vi cosine alpha, or fish, times t, and we already said that tf equals vi sine alpha over d, so the time is now t is equivalent to that times vi sine alpha over g equals x of f, which is that point right there, xf. Look at how far we've gotten. Yay. So, just going to let you take that in for a minute. Now, we actually can determine the point at which it'll land, given these two factors here, which equals x of f, or the final point of x. I'm going to do a quick example just to prove that to you, which, well, sorry, probably have to get. If you have a notebook, it probably would have been a good idea to write some of this down, because I'm not quite sure how well I'm doing, but that's your prerogative. Just a quick example. Let's say we threw it at a velocity of 100 meters per second, but it's